Okay, so we've talked about these nonlinear models, and now let's talk about how to actually fit them in R. And so recall we have different types of nonlinear models that we could be fitting. For example, we have polynomial models. So those will be ones like where you have x squared, x cubed, x to the fourth, et cetera, et cetera. So those will be polynomial models. And you can have basically k degree polynomial models where k is essentially the number of terms that you end up including for a given x variable, where they increment kind of by one the power that you're raising those values to. And then we can have step functions, and so this was sort of where instead of having these kind of smooth polynomials, we could think about splitting them at certain knots and having kind of these step functions where we fit essentially a line between a couple different points. And then we talked about linear splines that are a little bit more flexible than the step function. So instead of having just a constant kind of flat step between each point, we could maybe have a line between each point. So it would have a different slope between each of the knots. And then we talked about cubic splines, which essentially would fit a polynomial between each of the knots. But because it's this spline, it's going to have some extra nice features where essentially it's going to do some smoothing for us at each of those knots rather than having some potential discontinuity. And then finally, we talked about natural splines, and these are the ones that I use the most often in my research because they basically have, in my kind of experience, the best of all of the different the best of all of these different types of functions. Because the natural splines, often we fit natural cubic splines, and so we basically are fitting cubic polynomials in between a series of knots. But they have some extra restraints which make it good, especially for things like prediction models. And these restraints include that in the tails, where often polynomials can get a little funky, natural splines require that you're linear in those tails. And so that fixes that potential problem of polynomials. And then in addition to being linear in the tails, the natural splines also have the same restrictions as like the cubic splines because they're splines. And so that means that there's not going to be this discontinuity at the knots. We have continuity at those knots as well. So these natural splines, I think, are really the best case scenario for most cases. So as a reminder, this is kind of what this looks like. So the first one would just be a piecewise cubic where you can have this discontinuity at a knot. And just as a reminder here, on my x-axis is age, my y-axis is wage. And so the age here is the predictor, y here the outcome is wage. And I've set a knot here. I have a single knot at 50. And so here, the piecewise cubic is just going to fit a cubic polynomial on either side of this knot. But we have this discontinuity, which is not super great. And so we can fix this by creating a continuous piecewise cubic, which basically forces the points to meet at age, which is fine, but you still can have these little inflection points. And so the cubic spline basically fixes that by smoothing over it. And then the natural cubic spline adds that one extra piece that if we had multiple knots, it would end up forcing linearity in the tails, which is a really nice feature. So a natural cubic spline extrapolates linearly beyond the boundary knots. And so this adds 4 extra constraints that basically allows us to put more internal knots for the same degrees of freedom as a regular cubic spline. And it's really easy to do this in R. And so you can transform any continuous or numeric variable into a natural spline by using the step_ns function in a recipe. And then you can specify the degrees of freedom that you'd like to use for that variable using the deg_free parameter. And so here's a quick example. I'm using the auto dataset from the ISLR package, and I'm fitting just a simple model between miles per gallon and horsepower. But instead of fitting horsepower as just a linear variable, I want to use a natural spline, and I'd like to designate 2 degrees of freedom to this natural spline. And so how many degrees of freedom did I allocate to the horsepower variable? 2. And so instead of actually specifying that degrees of freedom parameter, you can actually use the tune function to tune this like we have in the other cases. And so now, instead of setting that to 2, I'm using tune so that I can look across a grid of degrees of freedom and kind of find the best one that fits my model best, particularly if I'm using the test error to assess that. That'll help me kind of pick the best way to fit this model. And so you're going to be using this function in the lab, which we're going to be completing on Thursday. So you'll get some practice with it then. But I just wanted to make sure you had seen kind of how to do this in R before that.